correspondingly, we can have companion matrices appearing in the rational decompositions, which are, big. So in that sense, the Jordan decomposition is more limited. However, if you're working over the real numbers, you can always factor into a product of linear or quadratic. And the irreducible quadratics, it turns out those correspond to what are called complex eigenvalues. And so those kinds of things can be broken down into, then you can use what's called a real Jordan form, which addresses the complex eigenvalues in terms of blocks, which are actually rotation dilation blocks. So every complex eigenvalue corresponds to a subspace, which is essentially described by a rotation and a dilation, possibly projection or something. But, okay, so here's one. We'll do this one. So 2 minus 1. I'm sure there's some things I've forgotten to tell you about the fx module that I'm going to regret not having told you. Like one of the things that's popping to the top of my head is that the fx module is pure torsion. So let's think about that. V is the fx modulus of set, right? So what does the primary decomposition theorem say? It says this is isomorphic to what? Your ring, right? With the free rank of R, direct product with the ring mod your first annihilator all the way out to your
direct product or
direct. Well, you can write direct sum if you want.
okay.
Yeah. There you go. But here, R is equal to fx, yeah? And this is indeed a vector space isomorphism, right? Because
Yeah.
these are both, well, it is an F module, so it is a vector space, right? So what would happen if R was not equal to 0?
If R was not equal to 0?
Yeah.
Like little r or?
Little r, yeah.
You just get a bigger dimensional vector space?
Right. It would mean your vector space is isomorphic to some non-trivial product of the polynomials over the field of scalars, but that's infinite dimensional.
Oh.
It's impossible. Like you cannot have a finite dimensional vector space isomorphic to
infinite.
The Cartesian product of polynomials.
Yeah.
That's nonsense. So that tells us the free rank of the fx module 0, which is to say it's pure torsion. So that means that we can, basically just kind of cross this piece out, right? Cross that piece out, and we're going to be able to decompose. So the decomposition theorem says the vector space is decomposable as fx module mod this, right? So what are we doing? So how do you describe an fx module? You've got an fx module with relations, right?
It's direct sum of its coefficients mod its
right. You
ring mod the coefficients.
Right. So you got a1x equal to 0. You got your a2x equal to 0, right? Amx equal to 0. These are the relations, right? Yeah. Which define that module. So
yeah, the matrix, yeah.
So we're essentially back in the situation we were at the start of today.
Yeah.
So.
Oh, so we're going backwards and building it.
But now instead of working with integer coefficients, we're working with field coefficients.
Yeah.
However, our matrix is one of the elements of the ring, so it's actually going to be a matrix of polynomials. One matrix do we look at in particular? We look at xi xi minus a. So that's going to give me x minus 2, minus 2, 1, minus 2, x minus 2, 1, 1, 1, x minus 5. So this matrix describes the fx module relations that correspond to this, to the transformation of that matrix.
So, what does that
Might
entail?
understand that, but
What does that entail when we do?
there's a gap in what I've said and what I've claimed.
Yeah. So yeah, what does that entail when we do the column row switches?
Right, so now we can do row and column swaps and see where it takes us.
Yeah.
So in this case, so I'm sorry, Adric, I feel like I'm missing something to say right here, but I can tell you this, that the column swap corresponds to changing a basis now. And the row swap, well, that's just switching the order of the relations, but, and then of course you do row operations, add the relations, but why, I guess the thing I'm missing at the moment is why is this the matrix of relations for, why is this the relations matrix for A? I don't know if I've ever quite come at it from this perspective. I think you should be able to argue that, I think.
Well, if that's the relations matrix, right?
Why should that be the, right, why should that be the relations matrix?
I mean, it's just roots, right? No,
Why would xi minus a be equal to 0?
Maybe when you like if you reduce row A and you multiply it by x, or you multiply it by xi, it gives you just roots.
Yeah, I mean, we'll do the calculation here, we'll get to the answer, and then the answer will have meaning.
Mm-hmm.
I'll be honest with you, at the moment I don't understand why we start here. I'm just following down the foot, you know?
Mm-hmm.
Which I'm sure has explained it in the many pages of that book. I will admit I don't remember offhand. Now, okay, so we're going to do the row operations and column operations. So the first thing I do here is I say that this is equivalent. Where this marker before it wastes my time. See, this is what I was going to ask you, Nicholas. Oh, you're fine. Like I'm going to call you to ask you to get more markers at Walmart. My markers are all dying. Yeah, I know. That's why I wanted to go to Walmart. That's what it was. So
you say you just can't get gas?
this is gas.
Yeah, the container for the gas.
Well, there was that too. I mean, did you find one? Did you find one?
Yeah.
No, I have no excuse to get Daniel his gas.
What?
No, I have no excuse to get Daniel his gas. So I think what happened here, Audrey, is I swapped. Looks to me like I swapped rows 1 and 3.
Yes.
All right. Now I'm going to do row 2 plus. I'm going to do, let's see here, row 2 plus 2 row 1. And row 3. Now watch this. This will be new. Check this out. X minus 2, row 1. See, we're working over the polynomial ring, so now we're allowed to multiply by ring, polynomials, by row operations. So 1, 1, x minus 5, 0.
There's a lot of paper, you gotta have paper.
That's just x?
To make it conceptual, it's really fast.
Row 2, x, row 2, row 1, this is x.
And now, let's see here, 2 row 1, that's 2x minus 10, plus, so that's 2x minus 9. And then I've got 0. So you see I zeroed that out, right?
Yep.
And
And then you get x minus 2 plus x4. Row 1, x minus 2 minus 2. But it's minus, so it's plus, so that's x, I think. That x in the middle.
yeah, so you get row 3, so we get a minus 2 minus x minus 2 times what was it?
The row 1, yeah, 1.
So the other
Minus.
minus can't, I think it's minus x.
Yeah.
And
X minus 5x, so that's a polynomial.
yeah, so what's x minus 2?
X squared minus 7 plus 10.
So we get x minus 2 times x minus 5, right?
Yeah.
And then we're x minus 5 minus that, right?
Yeah.
Which is x minus 5 minus x squared
7
plus 7x plus 10.
plus 7x? It's minus.
Yeah, I meant minus 1.
No, that's plus the other
But
one.
the minus distributes.
Oh, yeah, you got it.
So it looks like I've got a minus x squared plus
8.
yeah, I got 7x there, is that right?
It's either 8 or 6, and I'm betting on 8.
Did I look at the wrong matrix? Let me just pause. I was supposed to do this matrix. I think I did this one. That was my bad. Right, it should be based on this one.
I think row 3 is 1.
Yeah. 1 minus x minus 2. The row 1 was x minus 5.
Oh, okay.
So that's 1 minus x squared minus 7x plus 10, which is minus x squared plus 7x
minus 9.
minus 9, which is what I have in my notes, thankfully. Now, here's the thing that didn't pop out at us in our previous calculations today, which is once you get this,
Mm-hmm.
then you can use column operations to just, and since you have zeros here,
Mm-hmm.
it doesn't affect this at all.
Okay.
So we can just subtract column 1 from column 2,
And then x minus 5.
and x minus 5 column 1.
Yeah.
And so this immediately gets us to 1, 0, a 0, 0x, 2x minus 9, 0 minus x, and then minus x squared plus 7x minus 9. Right. Then what?
Would you add 2 and 3? Row 2 and 3?
Oh, yeah, very nice. So row 2 plus row 3.
Where's that?
So like generically speaking, see what you're going to face here?
Big roll of paper.
We're going to add. We're going to add it to 3 though, right? We're going to modify 3.
Yeah,
Row 3 plus row 2. So if you think about what this would look like for a more complicated example, you're looking for like a least common multiple of the row or column you're working on so that you can make them match up and cancel stuff out, you know?
Yeah, so that's x squared plus, or, no, that's x3 minus x6.
I think,
No,
are we adding? So minus x squared plus 9x?
Yeah, I got minus x squared plus 9x minus 18.
Yep.
And so I got like, I think it's like a 3 and a 6.
So what I then did was to swap columns 2 and 3. Because I like the, wait a minute,
Swap columns 2 and 3.
no I didn't get that. I subtracted twice column 2 from column 3. Column 3 minus twice column 2, right?
Yeah.
That's a nice move. Because that,
Minus 9, right?
yeah. Now I flip-flop the columns. The column 2 and column 3 switcheroo. And then I divided row 2 by 9, which I'm going to go ahead and do in this, don't try writing it, okay? I'm going to divide row 2 by 9, minus 9.
Yeah.
This is a 1. And then I'll do row 3 minus x squared minus 9x plus 18. I'm having trouble with the math here. RQ. I want to make that, I want to kind of clear that out, so if I
You would add that.
should add that, huh? See, that's the thing, you want to think about adding or subtracting, whatever. Anyway, so we make those cancel, right? So if I do this times 1, that matches. I need to subtract that.
Yeah.
Subtract that, yeah. Sorry. So then they cancel.
Yeah, but you get it's a 0 on that. Nice.
We still have our x over minus 9 there, right? But then then we get 0 minus, x over minus 9 times
I called it sigma.
x squared minus 9x plus 18, I think.
Yeah.
All right. And then we can use this one to clear out that. And we can multiply the last one by minus 9, and we can factor that. Just make it pretty.
U.
So I use that middle one to clear out the x over minus 9,
Yeah.
and then I multiply the third row by that. This is the Smith normal form of A. If you have the Smith normal form, you can write down other things like the rational canonical form for the matrix and such. Now, in the case that the matrix, I think in the case that the, so here, this is a rather special case. See here, there's no list of invariant factors, right?
Mm-hmm.
There's just the one. See, so this means that, so this was a,
Right there.
this was a, essentially, so the way I think of this is, we started with this, we started with thinking about a basis. You had like V1, V2, and V3. Those are the basis, which is analogous, the basis is analogous to the generators and the generators relations we started with today, right? And what this is saying is that if you want to, and so the game that's played here is building the vector space as a lingle direct sum of things. So the way we generate would be something like this, like, like that, direct sum. Where this, by this I mean the T-cyclic subspace generated by that. But, so, fine, but it turns out, because of this calculation, that in fact you can throw away two of your generators and just use one. Right? In fact, R3 is equal to, we could do it like this, I guess. Well, anyway, I don't want to say specifically E3. I'm just saying there is a vector such that, with respect to a cyclic basis, we can write, we can find a V such that V, AV, A squared V is a basis for R3. What's the minimal polynomial?
X cubed.
Yeah, you're looking at it right there.
Yeah.
It's x times x minus 3 times x minus 6. If we were to take a times, what would a minus 3 be?
A minus 3.
A minus 6 be. See what I did?
Yeah.
So I just subtract this. When you go back to the matrix world, 6 times the identity and 3 times the identity. So allegedly, if we multiply this times that, we'll get the zero matrix.
Can I trust you?
Yeah, I don't want to do it.
Yeah.
Because, but that should give us the zero matrix. Okay, so, this also tells me that the eigenvalues are 0, 3, and 6.
Yeah.
Which means that there exists P such that a P inverse AP is equal to 0, 3, 6. Like that. But I guess the rational canonical form here is less interesting. It's just, the rational canonical form is something like Q inverse A Q equal to 0, 1, 0, 0, 0, 1, and then, you know, what's this thing gives us, we had our x cubed plus 9,
Yeah.
x squared plus
18x.
18x, so
So there's
that,
a minus somewhere.
How much that?
Is it on the 9? I think it's on the 9.
no, yeah, you're right. I'm bad.
It's
here.
better. Thank you.
Yeah.
Yes. So that translates to 0 for the constant, minus 18 for the linear, and 9 for the quadratic spot. Because if we use the so that would be the rational canonical form of A. This would be the Jordan form of A.
Yeah.
So basis of eigenvectors, cyclic basis. It's not immediately obvious what vector, right? It's not at all obvious what vector V can be used to generate the cyclic basis, right? But Dummett and Foote explains a step-by-step algorithmic way of finding the basis from manipulating the original basis by following the column operations and everything. I have never taught it. I tried once, and it's just easier to try to figure out what this is directly.
Yeah.
Because what you can do is just, well, anyway, it's just easier to track it in terms of direct. I find it's easier in terms of direct linear algebra. So there's one. All right, so let's do some more examples.
Now here, when you do the rational canonical form, you have 0 for A naught, and then this AD. Oh, so you do the 1 line. Okay.
Yes, I'm just saying.
Yeah.
I'm saying it is the companion matrix of the minimal polynomial,
Yeah.
which is also the character. In this case, the minimal polynomial is the characteristic polynomial.
Yeah.
That was a rather special example. Example 2 is equally silly. So here we have the diagonal matrix 2, 0, 0, 3. So the whole program that we're engaged in right now is kind of, it's like, how do you figure out how to diagonalize a matrix? Let's start with the diagonalized matrix and like see how the method works. But here it is. So it's rather silly. But it may be constructed x minus 2, 0, 0, x minus 3. So what I did was I said C1 minus C2, which gave me x minus 2, 3 minus x, 0, x minus 3. Then I added the rows. Cancels the x's, right? Oh, I added row 1, I added to row 1, so that gave me 1.
And then you add columns.
Then I did row 2 plus x minus 3, row 1. I'm sorry, I didn't make a mistake here. Just a second. Row 1 plus row 2, so I had to put an x minus 3 up here too. So yeah. Now row 2 plus x minus 3 row 1. What's that get me to?
X minus 3 plus 3 minus x.
Whoa.
Yeah.
We can clear that out, right? And we've got 1, 0, 0. What you got there? You got x squared minus 6x plus 9 plus x minus 3. So that's x squared minus 5x plus 6, also known as
X 6 minus 1, 2, 1, 5, 3.
3, yeah. Which is totally unsurprising because
Yeah.
the eigenvalues are 2 and 3. So the minimal polynomial is x minus 2 times x minus 3.
Yeah.
Which is, again, the characteristic polynomial as well here. Example 3. If I have 3, 1, 0, 3 for my a, that gives me xi minus a equal to x minus 3 minus 1, 0, x minus 3. So I flipped columns 1 and 2. And then I did row 2 plus x minus 3 times row 1. Why is that helpful? Oh,
0.
yeah, because it makes that 0, doesn't it? Okay, minus 1, 0. And, well, we get x minus 3 squared here, don't we?
Yeah.
Which then is equivalent to 1, 0, 0, x minus 3 squared. So this already is actually the Jordan form. So the matrix was already given in Jordan form. And actually in the last example, this is also Jordan form. So Jordan form is the closest to diagonal we can get, essentially. All right? So like next time we meet, I will rip apart the Jordan form from start to finish, okay? The next time we meet, will just be about Jordan form for the most part. So what I'm hoping to wrap up today is just my comments on the rational canonical. Now this, though, see, so this is not diagonalizable.
Oh, because it's det 0.
Mm-hmm. Well, no, because it's got this 1 up here. So it's not, this is the Jordan form, it's not diagonal, so it's not diagonalizable.
Oh.
If the Jordan form of the matrix is not a diagonal matrix, it's not diagonalizable.
Okay.
That's how stupid the Jordan form is. Like, if you want to answer a question about the matrix, you can look at the Jordan form of the matrix, and if it's true for the Jordan form, it's probably true for the matrix. Many, many questions about the behavior of a matrix can be answered by looking at the Jordan form. Diagonalizability is one of those. But so this, of course, is what, x squared minus 6x plus 9, right? So the rational canonical form of this matrix is just the companion matrix of this silly thing, which is what? 0, 1, minus 9, 6. There you go. This is the silly rational canonical form for this matrix. All right. Example 4. If we have A equals to 0, minus 1, 1, 0, then you can take xi minus A. And I'm going to skip the steps this time. And that is in fact equivalent to 1, 0, 0 x squared plus 1. This is actually already the real Jordan form. For eigenvalue I. Or you could say plus or minus I if you want. I guess I could say plus or minus I. The rational canonical form is 0, 1. Worlds have collided. So in this case, the real Jordan form is the rational canonical form, because that is also the companion matrix. It's funny. I wasn't expecting that. Whoa. Whoa. So, whoa. So let me give you a jump start on me. I like the raw chicken. I like what's going to happen to that. Well, you know what I mean. I'm not one for eating raw chicken. I'm not Paul. Paul once fed me raw chicken. I've been harassing him about it for about 20 years now.
Yeah, our buddy had never grilled before and gave us raw burgers before.
Ooh.
And we were like, yeah, I'll put this back in the grill, bud. You're done grilling. You said when you become a dad, you might get the powers back.
He's only allowed to grow once he has children.
Yes. That's part of being a dad. But until then, no more grilling.
I remember when I was a teenager, or like maybe 12, I forget exactly, the parents started letting me grill, and I thought, wow, this is awesome. And then in retrospect, I realized, oh, that was nice for my dad. Now he doesn't have to grill. Should we do trick Daniel because he could get to play with fire outside for a while. It's gonna be fun. No, well, he does like to harass. He does like to complain about my. Can I? My jerky, yes. My substandard grilling, which he always blames on voodoo. So you got your 2, 2, 3, 3. And you'll forgive me if I don't write down all these steps, but if we take xi minus a, I'm sure we can figure out how to do it in less steps than I have in this piece of paper, right?
There's matrix calculators for sure.
Is there a web calculator for this? That's a good question. I don't know. Probably.
I would assume so.
But after, about 20 minutes of jibber jabber, you finally get this down to 1. And so finally we have an example. I'm not going to write all the zeros next time. So here we have a 1 of x is equal to x minus 2, x minus 3. And that is equal to a 2 of x, right? So here, the minimal polynomial is x minus 2 times x minus 3. And I think it's always the case that the product of the polynomials that appear on the diagonal in Smith normal form are the characteristic polynomial. So the characteristic polynomial here is x minus 2 squared and x minus 3 squared, which is just obvious if you look at the determinant. So don't feel like I've done you any great service by pointing out you can do 20 minutes of row and column operations over the polynomial ring to get that. So, recap here. Let's connect the Jordan form and rational canonical form. Already in Jordan form.
Yeah.
It's already the Jordan form. What's the rational canonical form here? So the rational canonical form, I think it depends on whether you're going to go Curtis's way or, the other way. So let me see if they have an example enough in here for me to decide.
This is Q, right? And that we've calculated.
So theorem 21 is the Smith normal form theorem. You can see there. Characteristic polynomial for companion matrix of A of x is A of x. I think if I read this correctly, I know that these are, I know I'm right about those being the invariant factors, but I'm not sure. trying to decipher it from here.
Sorry, well,
You're fine. Let's see. Here's a section of rational canonical form. He's got, you know, that companion matrix we talked about. It said matrix to be rational canonical form is the direct sum of companion matrices for the monic polynomials A1 through AM of least degree with that. Oh, okay, well, so direct form of the companion matrices for the A1 through AX. So that's it then. Okay, so that's it. So that means the rational canonical form, we're going to, is it number times of foot? We want like Q inverse AQ to be equal to the companion matrix for, oh, and my notation was what, A? I guess he uses C for companion matrix, right? C of x squared minus 5x plus 6, C of x squared minus 5x plus 6. It's a block decomposition, so that's like 0, 1, minus 6, 5, 0, 1, minus 6, 5, like that. People on your headphones are like, ah! It's fine. So there's that. Let's see here. So example 6. Here I gave us 2. So I'll tell you, this is the real Jordan form. From lambda equals to 2 plus or minus 3i. With one generalized eigenvector. In other words, this is the non-diagonalizable case of, it's like you've got a repeated complex eigenvalue and it's not diagonalizable over C. So this is pretty far into the weeds in terms of like a regular linear algebra course. You won't find many people actually, you know, explaining this, but if we were to look at xi minus a, all right, then I won't even write it down, okay? But that is going to be, it's going to work out to the following. It's going to work out to 1, 1, and then you'll have x squared. So this gives you x minus 2 squared plus 9. It gives us x squared plus minus 4x plus 13. And then another x squared minus 4x plus 13. Zeros elsewhere. Oh, my bad. It's not just that. It's So this means that the minimal polynomial is the characteristic polynomial, and it's that quartic.
Yeah.
And if I was to foolishly multiply that out, how many cubes? Minus 4 and minus 8x cubed. How many squares? 13, 26. 26 plus 16, 42. Love when that happens. And then how many x's? 4 times 13 is 52.
104.
52. What are we at? Minus 104. And
169.
it's 169. So this gives you the rational canonical form of this matrix. It's got a single block. So it looks like this. So we got a minus 169, 4, minus 42, 8. Fun fact, this is a matrix with eigenvalue 2 plus or minus 3i, which is not diagonalizable.
So Jordan forms tell you a lot.
Yeah, and also, well, the rational, like, the thing is both the rational canonical form and the Jordan, well, here it is in Jordan form, but it is in real Jordan form. Some people would say the Jordan form doesn't exist because this doesn't have, it depends on what your field is. If your field is reals or rationals, there are many people who would say there's no Jordan form because there are no real eigenvalues, so you can't talk about it. More open-minded folks say, well, you can talk about it, but you have to complexify it, and in that context it has a modified Jordan form. But people who are narrow-minded insist that eigenvalues must be from the field of you're working on, and you can't do this. And still call it the Jordan form. It's heresy. I've gotten in substantial arguments with people in Stack Exchange about this. I don't really care that much, but the cool thing is that this matrix is similar to that matrix. So anything I can see about this matrix is also true for that one. For example, the trace of this matrix, 2 plus 2 plus 2 plus 2 is 8. The trace of this matrix is 8. Not an accident. The trace of similar matrices is equal. The determinant of this matrix is the determinant of that times the determinant of that, which is 13 times 13 is 169. The determinant of this, you can easily see, is 169 if you're looking at the cofactor expansion across the top row. Plus, minus, plus, and plus, minus, plus, minus 169 times the determinant of any 169. Determinant's an invariant of similar matrices. Let's see here, what else can we show you? If we were to look at the 8, 1, 0, 0, 8, 1, 0, 0, 8 matrix, this is again a matrix in Jordan form. Alright, then you can look at xi minus a, and you can reduce it to, and I think I posted this for you, Audric, right? If you want to look at the steps. But I think you can figure out the steps.
That I'm confident in.
And I'm confident you can. But it works out for that. On the other hand, if we had, this is not my example 9 in the notes. Oh, fine, I'll do my example 9. I wanted to do example 8 tilde. So let's say A is 8000, 81008, all right? By the way, that's the Jordan block. Example 8 was a Jordan block. This is the Jordan 1 block of 8, direct sum with the Jordan 2 block of 8. This was straight up the Jordan 3 block of 8. But I believe if we did the Smith normal form calculation for this guy, we would get 1 x minus 8, x minus 8 squared. Because the minimal polynomial for this is x minus 8 squared. It's fairly easy to see that. If you subtract 8 times identity, you just get the 0, 0, 0, 0, 1, 0, 0 matrix. That matrix, if you square it, you get the 0 matrix. So you only need the square to kill off a minus 8I. So this is the minimal polynomial. And then the characteristic polynomial is clearly x minus 8 quantity cubed, so that means that has to be what's there. And then, perhaps interestingly, what's the rational canonical form here? So Q inverse AQ would look like, let's see here. So we've got, first of all, a 1 by 1 block. What's the characteristic? What's the companion matrix for x minus 8 look like?
0, 1.
You can't do it. It's a 1 by 1.
Oh, it's not 2 by 2? Oh, that's because that has to be x squared.
So
right?
what?
Yeah. So it would just be minus 8. Oh, you're right.
Yeah. So you put an 8 here. And then, of course, you know, x minus 8 squared, so it's just 8. Because it's minus the alpha naught.
Yeah.
In x minus 8 squared, x squared minus 16x plus 64, so we get 0, 1, minus 64, 16. That's the rational canonical form in that case. In contrast, the rational canonical form for example 8, I would need to calculate x minus 8 cubed, yeah? X minus 8 cubed is x cubed minus 3 times 8x squared minus 3 times 64x plus minus 8 cubed. So that gives us rational canonical form 0, 1, 0, 0, 0, 1. And you got yourself 8 cubed up there, 3 times 64, which is 192 minus 192, and then 24. So you can see things about the eigenvalues and the multiplicity of eigenvectors from the rational canonical form if you think about it. But information about eigenvalues and eigenvectors is manifest from the Jordan form. You have to kind of think about it more. The fact that there's 2 companion matrices here tells me that one of the factors was repeated like that, so that means that